One of humanity's most remarkable transformation over the past century has been lighting up the cities. From space, the sight is breathtaking. A glowing web of light that shouts, progress. But after the initial, wow, that's right, comes a second thought. Wow, that's a lot of energy. As city planners tackle the challenges of energy efficiency and safety, streetlight design has evolved dramatically in the past decade. Motion sensing technology now allows streetlights to dim when no one's around and brighten when movement is detected, saving massive amounts of energy while keeping vehicles and pedestrians safe. Welcome to Tech Chat, brought to you by Mouser Electronics. Stay tuned as we explore the latest innovation in smart cities and streetlight architecture. Welcome to Tech Chat, sponsored by Mouser Electronics. I'm your host, Xiangmiao Yuan. Welcome to today's presentation on smart city and streetlight architectures. Streetlights are evolving so fast in smart cities, and then it's perfect position to power a transformation in technologies. We will explore how TE connectivity creates the street lighting system to help this development. Special thanks to Mouser Electronics for sponsoring the session. Please welcome our guest today, Jonathan Catchpole. He's a system architect from TE Connectivity. Hello, Jonathan.
Hi, Meow.
Thank you for coming to our Tech Chat. We're super excited to learn more about the smart city street lighting and architectures. Please begin. Thank you.
Wonderful. Thank you. So as Meow said, I'm Jonathan Catchpole, a system architect at TE Connectivity, and I work in our lighting division. Today I'm going to talk about smart cities, street lighting architecture, and TE sensor solutions. Firstly, street lighting and smart cities. Smart cities and streetlights are often talked about in the same breath, as they are regularly positioned power supplies with a unique vantage point of a city, a perfect place to position a smart sensor. To achieve this, a city's luminaire needs to be smart ready. At TE, we worked with a lighting consortia called Zaga to create a standard called Book 18. Book 18 can be the backbone of smart city platforms, as it creates interoperability between luminaires, control devices, and sensors. We first released Book 18 back in 2017. Edition 1 spoke only of the mechanical fit system, but this was important. Until then, the only standardized connector interface was in the North American market. The interface controlled by ANSI was originally designed for incandescent light sources and not LED. Therefore, it's big, with a higher price point and difficult to seal. Zaga's Book 18 connector was the first and still the only connector designed from the ground up for LED street lighting. Edition 2 was released in 2019 when we went beyond a mechanical fit system and created the two-node architecture. By not only standardizing the mechanical interface, but the wiring architecture, the digital communication protocol, allowing a node on the bottom to talk to a node on the top and in turn control the driver, as well as defining the power budget that the luminaire must be capable of delivering to the two nodes. A certification program was also released at the same time. Certification ensures that luminaires and control devices are interoperable and will work together. So give a lot of confidence to the end user when they're specifying and installing these technologies. Edition 3 was released in 21 and allowed for the ANSI interface to be used, creating a hybrid two-node architecture. We're now working on Edition 4 that will enable other form factors beyond Cobra heads.
I see that on Edition 3, the hybrid architecture. Can you elaborate on the hybrid side? It's a hybrid of a sensor and something else?
Good question. So what makes this hybrid is that you'll see it on a future slide, but the hybrid architecture has the ANSI interface on the top of the luminaire and the Zaga interface on the bottom, whereas a standard two-node architecture has the Zaga on top and on the bottom.
And then this is just to help to make the streetlight truly smart. Is that correct?
So this to do with regionality. So in North America and, well, in the whole of the Americas and in areas like Southeast Asia, Australia and New Zealand, they have a preference towards the ANSI interface. So this was to allow, well, we never disallowed the use of the ANSI interface, but we never told a user how to wire it in. So edition 3 told the user how to create that hybrid architecture.
Yeah, so the functionality is always there, but it just depends on whether the user wants to enable it or not. Is that right?
Well, it's their preference over the connector interface. Prior to edition 2 being released, only the single node architecture existed in either the ANSI or the Zaga architecture. Traditionally, the ANSI architecture had been widely used with analog controls, so switching power to the driver to turn the light output on or off. The analog controls limits the functionality that can be achieved, and no downwards-facing interface rules out sensors that need a downwards field of view. On the left-hand side of the screen, we can see the ANSI and the Zaga interfaces. So this is the ANSI interface, and this is the Zaga. And the ANSI is considerably larger than the Zaga interface. On this slide, I'm showing the two-node architecture. So the D4i driver contains a DALI bus power supply and a 24-volt auxiliary power supply for powering the two interfaces. The driver is connected directly to the mains, unlike the ANSI architecture, meaning that the smart city sensor will be active during the daylight period and not just during the night. As shown, both interfaces are connected to the 24-volt rail and the DALI bus. For the communication between the two nodes, we needed a digital communication protocol. DALI was the obvious choice. Although it's a multi-master protocol, it had no hierarchy built into it. This means that if a photocell on top of the luminaire is telling the driver it's daytime, switch off, and there was a motion sensor on the bottom saying it has detected activity, switch on, we get strange behavior with the light source. Therefore, we created a flavor of DALI called D4i. This has the hierarchy baked in and uses either a Type A or a Type B device. Both Type A and Type B devices can contain an application controller. The application controller is the part of the software code that tells the driver what to do: turn on, turn off, dim to a fixed level. This means both types of device can control the driver when they are the only device plugged into the luminaire. Now, you can have a single Type A or a single Type B connected, and you can have a Type A and a Type B, but you can't have two Type A's or two Type B's. When you have a Type A and a Type B connected on the same bus, the Type B device will send a query asking if the Type A device is connected. If it gets a response, so i.e. there is a Type A device connected to the top of the luminaire, it will disable its own application controller and become a simple input-only device.
So essentially, we're trying to avoid the competition of signals, is that right?
Correct, yes.
The new driver design is ultimately trying to solve the problem of the computation by sensing, is that right?
So it's not the driver per se, it's the communication protocol that's used between the two control devices and the driver. So yes, you don't want two control devices both sending commands to the driver. The driver's not intelligent.
Yeah, the driver itself is not intelligent, but you're adding a digital control unit to make it smarter. That's brilliant.
Yeah. So the driver is just the client, and it just responds to whichever control device speaks to it last. So you only want one control device telling the driver what to do. So that's the hierarchy that we have baked into this D4i communication protocol. So this slide is showing the wiring architecture for that hybrid luminaire that we discussed earlier. So this is where you have the ANSI interface on the top and then the Zaga interface on the bottom. It's got the same wiring architecture. So we have the same wiring architecture. We still have the 24-volt rail, and we still have the DALI bus. It is the same kind of wiring architecture. But it's basically the same as the pure Zaga luminaire, but as with the single node architecture, the mains power is routed through the interface and the control devices. This is done for safety reasons, as the signal contacts on the ANSI interfaces aren't touch safe. An ANSI-based Zaga D4i control device can be a lot simpler than a traditional ANSI controller, as it doesn't need to have the mains power supply. It can have the mains power supply, but it doesn't need to have the one, and it doesn't need to have a switching relay. But it must have a permanent pass-through so that the driver is permanently powered and hence be able to power sensors in that second interface 24 hours a day, 7 days a week. So as TE, we'd spent a lot of time creating this platform, so we thought we'd better create something to plug into that second interface. And as others have done, a motion sensor was the obvious place to start, although we have a roadmap of other sensor types that we are working on at the moment. As pressures increase on our global resources, sustainability is at the forefront of consideration for many organizations like governments, municipalities, and even power utilities. But the main purpose of public lighting is to provide safety and security. Although for long periods of the night, there may be no activity. So these are areas that are being lit at full brightness, using energy with nobody benefiting from it. We're just burning energy for the sake of burning energy. Some local authorities, some municipalities have made the decision to turn lights off, even if for only part of the night, but there is a liability issue. So if an accident or an incident was to occur, that local authority could be liable for that incident. So with a motion sensor, there doesn't need to be that compromise. Energy savings can be made while still providing the main purpose of public lighting, safety and security.
Every time I, see a big bright street light just shining for no reason, like my heart bleeds a little bit. It's a lot of energy wasted for no good reason. Yeah, but as you said, the security is safety and security is a big concern. What would be the challenges for making converting a streetlight from traditional streetlight to a newer, like motion sense streetlight? Is there any concerns with the transformation?
So what we're advocating is cities future-proof their infrastructure by installing Zaga D4i luminaires. So these are luminaires with the D4i driver, with the two interfaces, whether they be Zaga Zaga or ANSI Zaga, and then they can plug whatever sensors they want into throughout the life of that luminaire. Luminaires typically have a useful life about 15 to 20 years, but you might want to update those controls as new products are developing, as new technologies come through. Best will in the world, a luminaire, its sole purpose is for lighting that patch of ground beneath it. So you're only ever going to want to turn that light on, turn that light off, or dim it to a certain level. But you might want to plug in other controls that do other things. Pollution monitoring is one thing we're working on. Traffic monitoring as well. So plugging cameras into these luminaires to monitor traffic flow and then use that information. The data they collect and the information that they collect may or may not affect the light output, but it's still very useful information, and we can still use that street light as that platform for smart cities.
Yeah, do you mean the streetlight can also function as like a data collecting tool for the city?
Yes.
Oh,
indeed.
That's great. Yeah, more data is always better. Yeah.
Indeed. So those reasons are why we created the LUMAWISE motion range. So as with indoor motion sensors, LUMAWISE motion can save energy and therefore cost by dimming the light levels during times of no activity, and then quickly restore to full brightness in response to motion. But LUMAWISE motion is designed specifically for outdoor and street light use. We released the original LUMAWISE motion about 2 years ago. The original version had fixed parameters that couldn't be changed by a user. Earlier this year, we released a version that can be user programmable, and it's user programmable via the DALI bus. as well as a version with analog controls. But I'll now take you through LUMAWISE Motion and LUMAWISE Motion Programmable. LUMAWISE Motion and LUMAWISE Motion Programmable are both part of the Xaga D4i ecosystem and are fully certified as such. They are both true Type B devices, which mean they contain an application controller and control the driver directly. Or if paired with a Type A device, will disable this application controller and just put motion events onto the bus for the Type A device to read out and then respond to that. LUMAWISE Motion uses PIR technology for motion detection, but also contains an ambient light sensor and uses this to turn the light on and off at dusk and dawn. The default values are 35 lux on, 18 lux off. These are fixed for the original version, but as I said, are fully programmable for the programmable version. Dimming levels are set to 20% for no motion and then 100% when motion is detected. The light will stay at 100% brightness for 2 minutes, then if no motion is detected, will return to 20% brightness. Again, all of these parameters are fully programmable in the newer version. LUMAWISE Motion has been tested on pole heights from 5 to 12 meters, but I'll talk about that more on further slides. Also has been tested on all forms of pedestrians, from walking, running, wheelchair users, cyclists. It will certainly detect vehicles. A combustion engine is a large source of infrared, but we haven't been able to test that. We do have customers that are using it in that application, so it will work in that. And then EVs are a bit of an unknown as well. We have made the device as compact as possible with an outer diameter of 80 millimeters. The electronics could be made smaller, but it's the optics that are dictating the size of that unit due to the market-leading detection zone we wanted to achieve. Book 18 requires a Type B device to pull no more than 46 milliamps. LUMAWISE Motion is powered from the DALI bus. So DALI is a powered communication protocol, and we use that power from the communication protocol to power the device. And LUMAWISE Motion is considerably below that 46 milliamp limit, drawing 25 milliamps on startup and then 6 to 8 milliamps during normal operation.
If there's no motion, it will be just using 20% of the brightness. Would this prolong the lifetime of the light?
It will do, yes. Yeah. So yeah, that's a good point. That not only are we saving energy, but you'd increase the life of the LEDs and the driver as well.
Basically, the control unit is running on a separate DALI protocol, and then is this also saving the energy? Is that right?
So DALI allows us to dim the light source. So the communication protocol has dimming curves programmed into it, so you can dim down to certain levels. But it's our motion sensor that is specifically saying dim down to 20%. But we send that command using the DALI communication protocol. So next, I'll talk about LUMAWISE Motion logic output. This is our analog version of the device. The logic output version has the same detection capabilities as the other two devices, but doesn't use digital communication. Instead uses a high signal to indicate that motion has been detected. This high signal must be processed by a control device on top of the luminaire, which will then control the light output. So with the digital communication, you could have just LUMAWISE Motion controlling the luminaire, but with analog control, you need a master controller on the top. Logic output, this version still contains the ambient light sensor, which can measure levels between 0 to 2000 lux, and then we give those measurements out as a logarithmic analog signal on the fourth pin of the connector.
Can you help us quickly do a comparison between the two versions? Like if maybe give us an example in what environment or setup that which version would be more suitable to that system design?
Analog controls have still been very popular in North America. So this kind of design was, we developed this thinking that the North American market would want to hang on to their analog control logic. There's a certain feeling that it's lower cost and it's more reliable. Whereas where I live over in Europe, everything is digital. So all lighting uses DALI, and all outdoor lights use DALI digital controls. So it's a regional difference, but we're starting to see, even in North America, that the digital communication DALI is making some gains in that market, and I think we might be on the cusp of North America switching over to digital from analog.
It will take some time to make the changes, but eventually, probably, yeah, we'll all convert to one type or the other. Yeah, thank you.
So LUMAWISE motion logic output has a different architecture. It's notionally got the name of Z10 architecture, which uses the ANSI interface on the top and the Z10 interface on the bottom. Logic output is powered from an auxiliary power supply in the NLC. So this was that master controller that you need in this analog architecture. Logic output is powered from an auxiliary power supply in that NLC control device on the top, and our LUMAWISE motion will accept an input voltage of 10 to 24 volts DC. The high signal from LUMAWISE motion is connected to the sensor pin of the control device, and upon motion being detected, a control signal, usually 0 to 10 volt, so this is that analog control that we just spoke about, is sent to the driver to dim the light output. Lastly, I want to speak to the performance of LUMAWISE motion product and its market-leading detection range. Typically, at a height of 5 meters, we get a detection range of about 15 meters. And I just want to show the audience a video showing the performance here. As you can see, the cyclist enters the shot at the bottom right of the screen. And if I scrub back to the moment the light transitions from 20% to full brightness, we can see that the cyclist is only just in the field of view. The luminaire is only 5 meters high, so it's quite a low luminaire. That cyclist is wearing a heavy coat, gloves, a helmet, and we were still able to detect him over 15 meters away. So we're super pleased with the performance that we've been able to achieve with this product, and that's across the whole range of our LUMAWISE motion sensors. So whether that's the digital or the analog version, and we believe that's market leading and market performance.
So it's the high sensitivity, and it's a key to safety, right? You don't want to miss the fast-moving object. Can you tell us, like, maybe a little more about, like, how is it possible to detect something moving pretty fast from far away?
I don't want to give away too many of our secrets.
Okay.
But,
yeah.
The designs of the optics is the critical thing. So we have custom optics that are specific for this application. We do see other products that have just used off-the-shelf lenses, and they don't get the same performance. There's a few things we've done in the electronics and the sensor selection and how we process the signal as well, which have all been done to maximize getting as large a detection pattern as possible.
Right. So it's tuned to, like, in-housely, to specifically for this for the system to be able to detect that. Yeah, that's very awesome. Yeah.
So like I said earlier, we've all worked in office buildings where we've had sensors in those office buildings, and they work very well in office buildings, but LUMAWISE motion has been designed specifically for this street lighting application and for outdoor use.
In the office setting and in the outdoor setting is completely different. Is the system also designed to withstand harsh environment? I know we have been having crazy weathers here in North America and then around the world. Is this unit also have a design aspect that's really good for that?
Yes, yeah. So it's IP68 We've also tested at IP66 and then impact resistance to IKO8, I believe, as well. TE has got a lot of history of designing products for harsh environments, and that's where a lot of our expertise lies. We have lenses designed for both rectangular and circular detection patterns. At a height of 5 meters, we get on this rectangular pattern, at a height of 5 meters, we get a detection range of about 30 meters by 6 meters, which increases as the pole height increases as well. The detection diagrams shown on the screen show only one half the detection pattern, but the sensor has a 360-degree field of view. So this rectangular lens is best suited for application like roadways, like cycleways, like pathways as well. But we also have lenses for a circular detection pattern for applications like parking lots, like recreational areas. So we've got different options depending on the application that somebody wants to install this in. The diagrams shown here are for the circular detection zone, and again, LUMAWISE Motion has an impressive 15-meter radius at a 5-meter height. And finally, I just want to sort of give a customer quote. We worked with a realty company which owns 450 shopping malls across North America and are very focused on sustainability. They stated that with LUMAWISE Motion, it had double the performance of the incumbent product they were using. Previously, they hadn't been able to dim the lights down to as low a level as they targeted because they had two bigger blind spots between the poles, between the lights. So they didn't want people walking through these blind spots. But with LUMAWISE Motion and with our very large detection area, they were able to achieve the dimming levels they wanted to, and I believe it was dimming down to 20%, and really get the energy savings that they were trying to achieve.
What advice would you give to maybe the other companies that's trying to innovate or build better system to adopt these lights? What would you recommend them to do when they switch to the system?
Like I said before, so I would absolutely always start with the Zagadi for Eye Luminaire. You've then future-proofed your system. You've got those two interfaces. You don't need to install. The beauty of the Zagadi for Eye platform is that you don't have to install the whole end-to-end solution on the same budgetary cycle. You can install the luminaires today with a simple photocell to give on and off control. You can then upgrade that a year later to add in connectivity. You could add a motion sensor, and as TE and other companies release other sensor types, you can then connect those to the luminaire as well. I've got one customer we work with in Australia, and they describe the Zagadi for Eye platform as the cheapest way to deploy citywide sensors. So literally, you just go with a box full of sensors.
Yeah, just go with it. Yeah.
Yeah, you get a cherry picker, go up to the luminaire, and just plug your sensor in, plug it in, and you're done.
Oh, I love it. It's just like once you adopt it, once you start with the system, you can have unlimited options, downwards. You can maybe put some system in, and then later on you might be like, oh, we need something else. We need a, better detection, or, this and that. You can always keep adding or keep subtracting and keep, changing it. That's amazing.
Yeah, and like I said, TE, we're working on different sensor types. Other companies are working on different sensor types as well. So it's really where our imagination drives us to the creativity that we can just plug a different smart city sensor into this luminaire, into this existing platform. And as TE, one of the phrases we use is we talk about turning your street light into an asset that goes beyond just lighting that patch of ground below it.
Yeah, I think that's part of the beauty of city planning. They can just make a basic light, or they can make it more efficient and more safe for everyone. What advantage do you have over other companies? I know you mentioned that other companies are also inventing different sensors and then maybe have a slightly different design from the architecture you just mentioned? Like, what advantage of your architecture design over those companies?
So LUMAWISE Motion, the advantage there is that market-leading detection area. So we have deliberately designed a product that just the detection area, just make it as large as possible. And in the custom lens and the things we did with the sensor selection and the signal processing of that has all been done to do that. But the advantage of working with TE is that we were one of the key people driving this standard development in Zaga. Myself, I sit on the Zaga committee. We drove the original edition 1 release, and we've driven edition 2 and edition 3, and now driving edition 4. So we have that inside knowledge of what this system should look like, and driving it to give future advantages to the user base.
Thank you, Jonathan, for showing us such an exciting product today.
Thank you, and thanks for the opportunity to share it with your watchers.
Thank you, audiences, for tuning in today, and a special thank you to Mouser Electronics. And please don't forget to go on mouser.com to check out more exciting products. Please check back in. We have more exciting products and more exciting news to share with you. See ya.